Welcome to this explainer. Today, we're diving into a really fascinating collision of two completely different worlds. On one hand, you have the strict, unyielding rules of pure mathematics. And on the other, the incredibly complex, nuanced science of figuring out if a student has actually learned those rules. It's a wild journey from abstract numbers to human comprehension, so let's break it down together.
So here is the big, overarching question that's going to drive everything we look at today. What does it really take to master the language of the universe? And maybe even more importantly, how do you prove you've actually learned it? Let's be real, whether you're a teacher or a student, it is simply not enough to just nod along what a formula is written on the whiteboard. There has to be a tangible, highly measurable way to translate that internal aha moment into concrete external proof. To get there, here's our roadmap for today. We'll start with the foundations of algebra and geometry. Then we'll look at mastering real-world word problems. From there, we'll shift into the statistics of success. And finally, designing effective math assessments. All right, let's jump right into Section 1, Foundations, Algebra and Geometry. When you get right down to it, an algebraic expression isn't just some dry jumble of random letters and numbers. It's actually a brilliant translation tool. By taking an abstract, completely unknown quantity and giving it a placeholder, usually the famous letter x, we give ourselves a way to systematically pin that unknown down. We're literally bringing order to the chaos by connecting these placeholders with simple operations like addition or subtraction. But here's the catch. Pure math demands a strict architectural structure. You can't just solve an expression however you feel like it on any given Tuesday. You absolutely have to follow an explicit blueprint. That's where acronyms like PEMDAS come in, dictating the exact order of parentheses, exponentiation, multiplication, division, addition, and subtraction. And it's not just algebra. Geometry relies on its own foundational rules, building upon seemingly simple, undefined terms like a point, a line, and a plane to eventually prove incredibly complex theorems. This brings us to a brilliant insight from Robert Gagne's theory of learning. He famously noted that learning is mainly a matter of accurate discrimination. Think about what that means for a math student. When they look at a massive polynomial or a complex geometric shape, their success depends entirely on their ability to accurately discriminate between different operations, variables, and rules. If they can't immediately spot the difference between an exponent and a coefficient, the whole structural house of cards collapses. Teaching isn't just showing students the rules, it's literally training their eyes to see the math. Which leads us perfectly into Section 2, Mastering Real-World Word Problems. Now, we all know the collective groan that happens when word problems are assigned. But solving a math word problem is essentially just a translation exercise. Students are tasked with taking the English language and translating it into algebra. The standard 5-step process is their guide. First, read the problem carefully. Second, identify the knowns and unknowns. Third, represent those unknowns with variables. Fourth, solve the working equation. And finally, check if the result actually makes logical sense. When you think about it, it's really just reading comprehension disguised as math. Let's look at a classic application that probably made you sweat in high school: motion problems. These are governed by the trusty formula, distance equals rate times time. You know the scenario. Two trains leaving stations 260 miles apart, traveling toward each other at different speeds. By using those 5 steps we just talked about, a student can assign a variable t to the time it takes for the trains to meet, set up an equation combining their speeds, and solve for exactly when they cross paths. It takes abstract rules and forces them into the real world. But as an educator, simply teaching this math is only half the battle. Accurately measuring how well your students have actually absorbed it, well, that's the other half. Let's transition over to Section 3, the statistics of success. Okay, so the big train test is over. You're the teacher, and you're staring at a mountain of raw data and a massive pile of grading. How do you make sense of it all? Enter descriptive statistics, specifically measures of central tendency. The mean, median, and mode aren't just boring vocabulary words you memorize and forget. They are an educator's ultimate survival toolkit. They offer the absolute fastest way to take the instant pulse of how the entire class performed as a whole. But wait, an average doesn't tell you the whole story, does it? What happens if the test scores aren't perfectly balanced? That brings us to skewness, which is just a fancy way of measuring how much our class data departs from a perfectly symmetrical bell curve. If a distribution is positively skewed, the tail extends way out to the right, which actually means most of your students got very low scores. That's a huge red flag for a teacher that the test was likely way too hard. On the flip side, a negative skew has a long tail to the left, meaning most students aced it and the test might have been a bit of a breeze. The truth is, raw test scores can be incredibly deceiving. That's why understanding standard deviation is so vital. Let's look at a specific student. We'll call him James Mark. In math analysis, he scored a 95. In labor management, a 94. And in natural science, an 80. If you just glance at the raw grades, math and labor management look like his strongest subjects, practically tied, right? But look closer at the z-score, which measures how many standard deviations his score is from the class average. His z-score in math is a positive 0.70, but in labor management, even with a 94, his z-score drops to only 0.27 because the whole class did well. Now, z-scores can get a little messy with confusing decimals and negative numbers, so to make this even easier to digest, educators often convert those z-scores into t-scores by multiplying by 10 and adding 50. It wipes out the negative numbers and gives us a clean, crisp metric. When we do the math, James Mark's t-score in math analysis calculates out to exactly 57. So despite his raw numbers looking pretty similar across different classes, the standard deviation and t-scores prove mathematically that his true performance relative to his peers was unequivocally the best in math. This kind of data is exactly what prevents unfair grading based on one overly easy or overly difficult test. There's another really cool visual way educators chop up the normal curve to ensure fair grading, and it's called stanines, which is just short for standard nines. This system divides the normal distribution of scores into 9 distinct parts. The broad middle covers 20% of the students, while the extreme high and low tails cover just 4%. It's a super quick, single-digit way to categorize a student's performance on a scale from 1 to 9, which makes score interpretation so much simpler for parents and students to actually wrap their heads around. Finally, let's wrap things up with Section 4, Designing Effective Math Assessments. So, we know how to measure the data once we have it, but how do teachers ensure the test they give is actually fair and accurate in the first place? They use what's called a table of specifications. A good teacher doesn't just sit down and randomly write 40 math questions. They use this blueprint. The test has to proportionally match the exact hours taught in class. Think about it. If you spent 2 weeks teaching parallel lines and only 1 day on linear equations, the items on the test need to reflect that exact time investment. It also guarantees a fair balance between simple memorization and higher-level, complex problem-solving. Now, when it comes to scoring more complex tasks, like a multi-step geometry project, teachers rely on rubrics. But they're constantly facing a really difficult trade-off here. Holistic rubrics look at the student's work as one big whole. They are super quick for the teacher to score and give a nice general overview, but they don't give the student much detailed feedback on how to improve. Analytic rubrics, on the other hand, break the final project down into individual component parts, scoring each one independently. They provide incredibly rich, actionable feedback, but they take an agonizing amount of time for the teacher to grade. It's a constant balancing act. But here is the ultimate reality check for any educator. All the formulas, perfectly balanced tables of specification, and highly detailed rubrics in the world are completely useless without one thing: validity. Validity simply means the assessment actually measures exactly what it claims to measure. For example, if a math test is packed full of incredibly dense, overly complex vocabulary, the teacher might accidentally be testing the student's reading comprehension instead of their mathematical skill. Whether you're looking at content validity, concurrent validity, or predictive validity, the test absolutely must be a true reflection of the targeted learning. And that leads us to a final, slightly provocative thought to end this explainer. When we design these highly rigorous tests, when we calculate standard deviations, and when we apply our beautifully detailed rubrics, are we truly testing a student's deep mathematical intelligence and spatial reasoning? Or are we sometimes just testing their ability to memorize and blindly follow a rigid formula? It's the ultimate challenge of the educator's equation, and it's definitely something worth pondering as you continue your own learning journey. Thanks so much for exploring this with us today, and keep asking those big questions.